Right now, something extraordinary is unfolding just beyond our view. For weeks, astronomers have been tracking a rare interstellar visitor called 3I Atlas, a green glowing comet from another star system. At first, the fascination was its alien chemistry and impossible trajectory. But now, the story has deepened. New objects, asteroids, comets, fragments seem to be appearing around the same time, multiplying across the sky as if the solar system itself has entered a new phase of activity. Our quiet neighborhood has turned into a corridor of motion. Dust, ice, and rock are crossing paths in patterns that test the limits of coincidence. Is it chance, a trick of our sharper telescopes, or is 3I Atlas a visible edge of something larger, a messenger arriving not alone, but as part of a greater pattern? In this video, we'll follow the trail of 3I Atlas and the sudden surge of companions around it, what we know, what we suspect, and what it could mean for Mars, Earth, and our understanding of the galaxy. And before we go any further, make sure you subscribe so you don't miss the rest of this story. Leave a comment telling us where in the world you're watching from, because just like these interstellar travelers, we too are connected across distance, sharing the same sky. The night sky has always been a symbol of permanence. For millennia, humans have looked upward and seen the same constellations tracing the same patterns, reliable as the seasons. Planets wander slowly, the moon waxes and wanes, and comets appear as rare messengers, streaking across generations. But in recent months, astronomers have noticed something that disrupts this sense of stability. A subtle but undeniable shift has taken place, a sudden increase in objects appearing in our skies, all while a rare interstellar visitor, 3I Atlas, draws near. At first, the changes were easy to dismiss. Astronomers regularly catalog new asteroids and comets. On average, several are discovered each week. With the power of modern telescopes and global surveys, such detections are expected. Yet, in August and September of 2025, the rate of discovery began to spike. Dozens of new objects were reported in quick succession, some passing surprisingly close to Earth, others aligning suspiciously with Mars's orbital corridor. The clustering was enough to raise questions. Was this simply coincidence, or was something larger unfolding? The timing could not be ignored. 3I Atlas, the third confirmed interstellar object ever detected, was making its approach. Unlike Oumuamua, which slipped past us almost unnoticed in 2017, or Borisov in 2019, which behaved much like a standard comet, Atlas carried a distinct signature. Its vivid green glow, caused by the breakdown of diatomic carbon in its coma, marked it out immediately. Its chemistry was different, its path hyperbolic, and its arrival coincided with a sudden parade of other celestial bodies. Astronomers debated the connection. One possibility was purely observational. Our instruments have grown sharper. The Vera Rubin Observatory was coming online, scanning vast swaths of the sky with unprecedented precision. Perhaps the surge in discoveries was simply the result of better detection. The universe had always been this busy, and only now could we see it clearly. But others argued the timing was too uncanny. The objects weren't just random. Their orbits seemed to thread through regions of space influenced by Mars, and indirectly by the incoming path of 3I Atlas. To the public, headlines spoke of a sudden swarm and a shift in the sky. Social media amplified the sense of drama, with amateur astronomers posting long exposure photos that showed faint streaks of new visitors alongside the emerald glow of Atlas. The night sky, once thought of as quiet and predictable, began to feel restless, alive with motion. From a scientific perspective, the implications were profound. If the clustering of objects was real, it could suggest gravitational disturbances, perhaps subtle nudges from Mars, or even the influence of 3I Atlas itself as it passed through the solar system. While its mass is far too small to alter planetary orbits, the presence of fragments, dust, and cometary debris might interact in ways we do not yet fully understand. The deeper question, though, was philosophical. Humanity has long relied on the illusion of stability in the sky. The stars were the fixed points by which we navigated both physically and spiritually. To see that stability give way to witness a sudden shift in the traffic of comets and asteroids is to be reminded of our vulnerability. The solar system is not a static stage, but a dynamic arena, constantly shaped by forces beyond our control. For astronomers, the shift was not cause for fear, but for urgency. Every new object cataloged adds to our understanding of how matter moves through space, how planetary systems evolve, evolve, and how often interstellar visitors pass our way. Each detection sharpens the tools of planetary defense and deepens our sense of connection to the galaxy. For the rest of us, the shift is a reminder to look upward, to remember that the night sky is not fixed, but alive, and that sometimes change comes suddenly carried on the faint green glow of a comet born around another star. Astronomical discoveries often arrive quietly. A faint streak appears in a telescope's field of view, a pattern of pixels registers on a digital sensor, or a subtle shift in brightness hints at something new. At first, there is no fanfare, just data, numbers, and a scientist double-checking what they see. Yet, sometimes, within those quiet beginnings lies the start of a story that will ripple across the world. So it was in July 2025 when 3I Atlas was first recognized for what it truly was, a visitor from beyond our solar system. The discovery came from the Atlas Survey, the Asteroid Terrestrial Impact Last Alert System. Designed to scan the skies for potential threats to Earth, Atlas consists of a network of wide-field telescopes capable of detecting faint, fast-moving objects. On a cool July night, the survey picked up a dim, greenish point of light moving against the backdrop of stars. At first, it seemed like another comet, one of hundreds catalogued every year. But its motion was strange. It was moving too fast, on a path that could not be explained by the sun's gravity alone. Orbital calculations soon revealed the truth. This object was not bound to the solar system. Its trajectory was hyperbolic, meaning it came from interstellar space and would never return once it passed by. Only two such objects had ever been confirmed before: Oumuamua in 2017 and Borisov in 2019. Now, 6 years later, astronomers realized they were witnessing the third, 3I Atlas. The timing could not have been more significant. July was already a month of heightened astronomical activity, with multiple asteroids passing unusually close to Earth. As the news spread that another interstellar object had entered the solar system, excitement surged. Scientists around the world redirected their instruments, eager to capture early data before the comet brightened and its coma expanded. The first images showed something remarkable. Even at great distance, the object glowed faintly green, a color linked to diatomic carbon molecules breaking apart under sunlight. This was unusual, even by comet standards, and it immediately suggested that 3I Atlas carried chemistry different from anything common in our solar system. In the following days, amateur astronomers began to capture long exposures, confirming the glow. For the first time, the public could see evidence of an interstellar traveler, not as a theoretical orbit on a chart, but as a visible, shimmering presence in the night sky. The scientific community responded with urgency. The James Webb Space Telescope was quickly tasked with gathering spectra. Hubble pointed its aging but still powerful mirror toward the comet. Ground-based observatories from Chile to Hawaii joined in, each chasing precious photons of light reflected off an object that had crossed unimaginable distances to reach us. Early data revealed elevated levels of nickel, an element not usually so dominant in comets. The imbalance between nickel and iron puzzled researchers, hinting that this object's birthplace may have been a stellar environment unlike our own. The July discovery was more than just another entry in the catalogs. It was a reminder that the solar system is open, porous, and constantly receiving visitors. For every 3I Atlas we detect, there may be countless others that pass unseen, too faint or too fast to be noticed. That realization alone carries weight. The galaxy is full of wanderers, and Earth is not isolated from their journeys. For the public, July 2025 became a moment of shared wonder. News outlets spoke of a new interstellar comet, while social media filled with speculation and awe. People who rarely looked at the night sky found themselves reading about hyperbolic orbits, diatomic carbon, and galactic wanderers. In the quiet glow of a green point of light, astronomy leapt from observatories into living rooms. The July discovery did not end with identification. It began a chain of events that continues to this day, a surge of new detections, debates over coincidence versus causation, and the unfolding drama of a comet whose story is still being written. But that first moment, in the stillness of July, will always stand as the turning point, the instant we realize that another messenger from beyond the stars had arrived. Every comet we have studied until now shares a common story. They were born in the distant reaches of our own solar system in the Kuiper Belt, or the Oort cloud vast reservoirs of ice and dust left over from the birth of the Sunday. These These comets circle back after eons, drawn inward by gravity, and remind us of our origins. But 3I Atlas is different. It does not belong here. Its orbit, its chemistry, and its speed all mark it as a true outsider, a visitor from beyond. From the moment astronomers plotted its trajectory, the evidence was clear. This object was not bound to the Sunday. Instead of a closed elliptical orbit, it traced a hyperbola, a curve that would bring it in close, let it swing around the sun, and then send it back into interstellar darkness, never to return. Its velocity, too, was revealing. Even far from the sun's pull, 3I Atlas moved faster than any native comet could. It carried with it the momentum of another star system, proof that its journey began light years away. This realization placed 3I Atlas in rare company. Only 2 other objects had been confirmed as interstellar before it. Oumuamua in 2017, a strange elongated rock that defied easy classification, and 2I divided by Borisov in 2019, a comet that looked more familiar but came with its own chemical surprises. Now, in 2025, came the third, a vivid green comet whose very glow spoke of chemistry alien to our system. What makes an interstellar comet so important is not just its rarity, but what it represents. Each one is a fragment of another star's history. Long ago, in some distant system, planets were forming. Gravity sculpted disks of dust and gas into worlds, moons, and debris. Giant planets stirred the outskirts, scattering comets into unstable paths. Some of those comets were flung outward with such force that they escaped their home star's gravity entirely. They became interstellar wanderers, drifting through the galaxy for millions or even billions of years until chance brought them near another Sunday. That is how 3I Atlas came to us, a survivor of ancient chaos, a piece of a world we will never see. Its chemistry underscores this alien origin. Spectroscopic studies revealed an unusual abundance of nickel compared to iron, a ratio different from comets formed in our own system. Its coma shone green from diatomic carbon, giving it an eerie hue uncommon in local comets. These signatures suggest that it was born under conditions unlike those of our solar nursery. In a way, it is a message in a bottle, carrying the fingerprint of its birthplace across light years. The implications are profound. By studying 3I Atlas, astronomers are not just learning about a comet, they are learning about planetary formation in another star system entirely. Its composition offers a rare point of comparison, helping us understand whether our solar system is typical or unusual. Each molecule detected, each ratio measured, is a clue to processes that unfolded in a stellar neighborhood far beyond our reach. To the public, the idea of a visitor from beyond captured imagination in a way few scientific discoveries do. The night sky, once thought of as fixed and familiar, suddenly contained a traveler from another Sunday. People asked what it meant. Was it dangerous? Could it carry life's ingredients from one system to another? Could such visitors be common, passing unnoticed through our skies every decade? The questions spilled outward, faster than the answers. For scientists, though, the focus was clear. This was a chance too rare to waste. Observatories across the globe coordinated observations, knowing that the window would be brief. In a few months, the comet would dim and vanish, retreating forever into interstellar space. Every night mattered. In the end, what defines 3I Atlas is not its brightness, its color, or even its chemistry, but its story. It is a reminder that our solar system is not an island. We are part of a galaxy where fragments of other worlds drift through ours, carrying with them whispers of alien histories, and for a short time, we are lucky enough to witness one. When astronomers realized that 3I Atlas was interstellar, their thoughts immediately turned to the only 2 visitors of its kind we had seen before. 1I Oumuamua, and 2I divided by Borisov. These past strangers had passed through our solar system like brief actors on a stage, offering tantalizing glimpses into other star systems before disappearing forever. Each taught us lessons, some expected, others surprising, and those lessons are shaping how we now approach 3I Atlas. The first, Oumuamua, arrived in October 2017. It was small, faint, and strange. Unlike like a comet, it showed no tail, no coma, no visible outgassing. Instead, it appeared as a bare rock tumbling through space, its brightness fluctuating as if it were elongated like a cigar or flat like a pancake. Most perplexing of all, it accelerated slightly as it moved away from the sun, but without releasing visible jets of gas. These mysteries led some to suggest it could even be artificial, a fragment of alien technology, a thin solar sail, or debris from a long-lost civilization. While most scientists lean toward natural explanations, the debate revealed how unprepared we were to interpret the unexpected. Then came Borisov in 2019, where Oumuamua had been mysterious. Borisov was familiar. It looked and behaved much like a typical comet, with a bright coma and tail streaming outward under solar heating. But closer inspection revealed differences. Its chemical composition contained more carbon monoxide than most solar system comets, hinting at formation in a colder, perhaps more distant region of another star's protoplanetary disk. Borisov reassured us that interstellar comets could look normal while still carrying chemistry distinct from our own. Together, Oumuamua and Borisov framed the possibilities. Interstellar visitors could be enigmatic, forcing us to question our assumptions, or they could be ordinary, offering direct comparisons to the comets we know. Either way, they were invaluable. Both, however, arrived with one frustrating limitation: timing. They were discovered late, already near their closest approaches, giving astronomers little time to prepare or coordinate observations. By the time instruments were aimed and debates settled, the objects were fading. Their secrets slipped away almost as quickly as they arrived. That is what makes 3I Atlas so important. Discovered earlier in its approach and brighter than either of its predecessors, it gives us time to gather spectra across multiple wavelengths, time to map its coma and tails as they evolve, time to coordinate observations from Earth, space telescopes, and even Mars orbiters. In learning from the past strangers, astronomers now know what questions to ask, what data to prioritize, and how to avoid missing opportunities. The first lesson is vigilance. Oumuamua showed us that interstellar objects can appear suddenly and vanish just as quickly. Surveys like Atlas and the upcoming Vera Rubin Observatory are designed to catch these wanderers sooner, ensuring we are no longer caught by surprise. The second lesson is chemistry. Borisov reminded us that familiar shapes can hide exotic origins. With 3I Atlas, every molecule detected will be compared against our growing library of alien fingerprints. There is also a larger lesson, one that goes beyond data. Each interstellar object is a reminder of scale. Our solar system is not a closed world, isolated in the galaxy. It is porous, open, and connected. Material flows between stars, carried by gravity and time. These visitors are not intruders. They are threads in a vast galactic fabric, linking one system to another. As we study 3I Atlas, we carry the memory of Oumuamua's riddles and Borisov's chemistry. We know now to expect the unexpected, to prepare for surprises, and to understand that no single visitor will tell the whole story. But each adds a piece, and one day, when enough pieces are gathered, we may finally see the full picture of how planetary systems across the galaxy are born, evolve, and share their materials. In this sense, the past strangers were not just fleeting curiosities, they were teachers, and because of them, we are better prepared for the lessons that 3I Atlas is now delivering. By late summer 2025, astronomers were beginning to notice something unusual. The discovery of 3I Atlas had already captured global attention, but alongside it came a series of smaller announcements, asteroid after asteroid, some no larger than city blocks, being detected as they passed near Earth or Mars. Normally, such discoveries are routine. Dozens of new objects are catalogued each month, part of the steady hum of survey work. But this time, the rhythm changed. Instead of a slow trickle, the reports arrived like a drumbeat. In just a few weeks, more than a dozen new near-Earth objects had been logged, a clustering that stood out against statistical expectations. To astronomers, the sudden surge felt like a parade. One by one, small asteroids appeared on detection screens, their orbits quickly calculated and shared with the minor planet center. Most were harmless, passing at safe distances measured in millions of kilometers. Yet, the timing of their discoveries, so close together and so near the arrival of 3I Atlas, raised eyebrows. Was this a coincidence born of better telescopes, or were we witnessing a genuine increase in celestial traffic? The Vera Rubin Observatory story played a central role. Although still in its early operational phase, its powerful, wide-field surveys were uncovering faint objects that older telescopes might have missed. That alone could explain part of the spike. As our instruments improve, the universe often appears busier, not because it has changed, but because our vision has sharpened. Yet even accounting for this, the clustering seemed uncanny. Some of the newly discovered asteroids were passing unusually close to Mars, threading through orbital corridors that mirrored the path of the incoming comet. Speculation grew. Could fragments related to 3I Atlas be arriving alongside it? Comets are known to shed debris, sometimes producing showers of meteors when Earth crosses their trails, but in this case, the objects appeared too large and too distant to be simple cometary fragments. Instead, scientists considered another possibility: resonance. The gravitational fields of Mars and Jupiter can create zones where asteroids cluster temporarily, moving in loose formation before dispersing. Perhaps the approach of 3I Atlas had coincided with one of these natural groupings, amplifying the sense of a parade. For planetary defense experts, the moment was sobering. Though none of the objects posed an immediate threat, their sheer number underscored how crowded the inner solar system can become. Earth exists in a cosmic shooting gallery, shielded only by constant vigilance. The September wave of detections pushed tracking networks to their limits, testing how quickly orbits could be calculated and risks communicated. In that sense, the parade was not just a curiosity, but a live exercise in planetary defense readiness. For the public, the story carried a different tone. News outlets reported on the asteroid surge with a mix of fascination and unease. Headlines hinted at omens, coincidences, and cosmic mysteries. Social media buzzed with images comparing the wave of detections to beads on a string, all aligned against the backdrop of Mars and the green glow of 3I Atlas. For many, the idea of multiple visitors arriving together, comets, asteroids, fragments, blurred into a narrative of cosmic drama. The truth, as always, lies between science and perception. Statistically, clustering can happen. Asteroid discoveries are not evenly distributed. Sometimes they arrive in waves due to observational conditions, telescope time, or orbital alignments. Yet, the coincidence with 3I Atlas kept the sense of pattern alive. Even seasoned astronomers admitted that the timing was striking, though likely natural. Still, the parade of asteroids added a layer of richness to the story. 3I Atlas was no longer an isolated figure, but part of a scene in which many actors crossed the stage at once. Dust, ice, and rock all seemed to be in motion, reminding us that the solar system is never quiet, never static. The parade may have been chance, but it was chance with meaning, a reminder of the traffic that surrounds us and of the vigilance required to understand it. In the end, the asteroids passed harmlessly, leaving behind only data and curiosity. But for those watching, the memory lingers. A season when the sky seemed busier than ever, when wanderers lined up like a cosmic procession, and when a green interstellar comet marched at the center of it all. Amid the growing attention on 3I Atlas and the wave of asteroids appearing in late 2025, another unexpected player entered the story: Comet Swan. Named after the solar wind anisotropies camera aboard the SOHO spacecraft, which first detected its outbursting fragments, Swan was not a new discovery. It had been catalogued before, a modest comet expected to pass quietly through the inner solar system. But in September, just as the sky was filling with new arrivals, it brightened dramatically, an eruption that caught even seasoned astronomers off guard. The timing could not have been stranger. As 3I Atlas approached Mars and telescopes tracked the multiplying objects in its wake, Swan flared in brightness, its coma expanding and its tail stretching visibly across long-exposure photographs. What should have been an ordinary, dim comet suddenly became an object of fascination. For a few weeks, it rivaled even the great interstellar visitor in the headlines. Astronomers were quick to investigate. Cometary outbursts are not unusual. Chunks of ice and dust on a comet's surface can crack, exposing volatile ices to sunlight, which erupt into gas and brighten the coma. But Swan's behavior seemed extreme, even by cometary standards. Its brightness increased tenfold in a matter of days. Telescopes equipped with spectrographs detected strong emissions of water vapor, cyanogen, and carbon compounds, suggesting a large patch of surface ice had suddenly destabilized. To the public, the coincidence was irresistible. Two bright comets, one interstellar and one homegrown, both active in the same season. Social media filled with side-by-side images, the eerie green glow of 3I Atlas next to the blue-white shimmer of Swan. Amateur astronomers delighted in the spectacle, pointing out that such overlap is rare. Most years pass without a naked-eye comet at all, yet in 2025 the skies had delivered two at once. The overlap raised questions in the scientific community as well. Was Swan's flare connected to the same gravitational and solar conditions influencing the September asteroid wave and the activity of 3I Atlas? Or was it pure coincidence, a reminder that comets are unpredictable and often surprise us without warning? The simplest explanation was the latter. Comets, after all, are fragile. Their surfaces are riddled with cracks, their interiors layered with volatile ices that can erupt chaotically. But even scientists admitted the timing made it feel as if the solar system had conspired to put on a show. Beyond the spectacle, Swan's eruption offered valuable data. The sudden release of gases gave researchers a chance to study fresh material from the comet's interior, pristine ices that had been shielded from sunlight for billions of years. Comparing this chemistry with that of 3I, Atlas revealed striking contrasts. Where Swan carried the familiar signatures of solar system comets, 3I Atlas displayed alien ratios, particularly its abundance of nickel and carbon dioxide. Together, the two formed a natural experiment, one local, one foreign, both shedding light on the diversity of comets across the galaxy. For planetary defense networks, the event was also a reminder of unpredictability. If a modest comet like Swan could flare so suddenly, releasing dust and fragments into new trajectories, it underscored the need to constantly monitor even familiar objects. What we assume will be faint and uneventful can, under the right conditions, transform into something far more dynamic. Culturally, the pairing of Swan and 3I Atlas rekindled a sense of cosmic wonder. People around the world stepped outside to watch, some for the first time in years, tracing glowing streaks with binoculars or telescopes. For many, the sky had come alive in a way it rarely does not with a single comet, but with a duet, two wanderers performing at once. By October, Swan faded again, its outburst settling into the background of ordinary cometary activity, but its surprise appearance had already left a mark. It had reminded us that the solar system remains full of hidden potential, that even familiar objects can defy prediction, and that sometimes the universe gives us more than we expected. Together with 3I Atlas, Swan turned the late months of 2025 into a season of celestial drama, one comet local, one interstellar, both reminding us that the cosmos is restless and that surprises can arrive when we least expect them. Astronomy is a science built on patience. Objects move slowly, orbits unfold over centuries, and events repeat with a predictability that reassures us. But every so often, patterns emerge that seem too precise, too coincidental, to be dismissed as random. In late 2025, as 3I Atlas drew closer to Mars, astronomers began to notice such a pattern. A cluster of new discoveries, asteroids, comets, outbursts, even unusual meteor showers appeared not scattered at random, but concentrated in ways that hinted at deeper connections. The first red flag was the asteroid surge. In just a matter of weeks, more than a dozen near-Earth objects were detected, many on paths that brushed past Mars or threaded uncomfortably close to Earth's orbit. That alone was remarkable. But when Comet Swan erupted at the same time, followed by smaller outbursts from lesser-known comets, the coincidences piled higher. Suddenly, the night sky was not just busier, but patterned a sequence of arrivals unfolding against the backdrop of the interstellar visitor. Statistical models are designed to test such perceptions. When scientists ran the numbers, some argued the clustering could indeed be coincidence. After all, surveys were more powerful than ever before. The Vera Rubin Observatory had come online, detecting faint objects that previous generations of astronomers would have missed. Perhaps the pattern was nothing more than improved vision, a human tendency to find order in noise, but others were not convinced. Even allowing for sharper telescopes, the timing and alignments looked too neat. The orbits of several of the new asteroids intersected near the same regions of space, creating temporary corridors of traffic. Some passed through gravitational resonances with Mars, as if guided by invisible rails. Meanwhile, 3I Atlas traced its hyperbolic path through the same celestial neighborhood, its emerald glow cutting across the same fields. To see so many objects converge in such a short span gave the impression of choreography rather than chaos. Astronomers debated debated the mechanisms. One possibility was resonance with Jupiter and Mars, which can cause small bodies to cluster before scattering again. Another was fragmentation. Perhaps some of the newcomers were pieces of larger objects that had broken apart long ago, now arriving in sequence like beads on a string, and in the background loomed the question of 3I Atlas itself. Could the interstellar visitor have brought fragments with it? Its hyperbolic trajectory made it unlikely to be gravitationally tied to the local objects, yet the human mind struggled to separate its dramatic arrival from the sudden parade surrounding it. For planetary defense teams, the pattern was a serious test. Each new discovery required rapid analysis to rule out danger. None posed a direct threat, but the clustering underscored how difficult prediction can be when multiple bodies cross similar regions of space. One error in calculation could mean underestimating the chance of impact. In that sense, the apparent pattern became an exercise in readiness, a rehearsal for scenarios in which multiple threats might appear at once. For the public, the narrative took on a different flavor. News outlets spoke of a cosmic alignment and patterns beyond chance. Social media amplified speculation, weaving theories about hidden connections, galactic tides, or even deliberate design. The truth was likely far simpler, rooted in physics and probability. Yet the impression of order mattered. It made people look upward with renewed attention, wondering if they were watching the universe reveal some hidden rhythm. In the end, the clustering may well have been coincidence. Astronomers know that randomness often produces streaks and clusters that look meaningful but are not. Yet the episode revealed something important about how we interpret the cosmos. We do not simply record data, we search for meaning within it. Patterns remind us that the universe is not static, that chance and order coexist in ways we still struggle to understand. For 3I Atlas, the timing of its arrival with the asteroid wave, with Swan's eruption, with meteor showers and minor comets, will forever be part of its story. Whether the connection was real or imagined, the impression remains. For a brief season in 2025, the sky itself seemed to pulse with activity, a pattern that defied the comfort of chance and made us wonder if the universe had more to say than we were prepared to hear. While Earth has been busy watching the skies, it is Mars that has become the true stage for this unfolding drama. The red planet, orbiting at just the right distance and angle, lies close to the projected path of 3I Atlas. From Earth, the comet glows as a faint green point in the night sky. But from Mars, the encounter is far more immediate. The planet stands in the direct spotlight of the interstellar visitor, and the world is watching to see what happens next. Mars is uniquely suited to play this role. Unlike Earth, its surface preserves scars from countless impacts. Its thin atmosphere provides little protection, allowing even small meteors to carve craters into its dusty plains. If fragments of 3I Atlas were to break off, Mars would be far more vulnerable to strikes than Earth. For planetary scientists, this creates both risk and opportunity. An impact could alter the Martian surface in ways we could study for decades, giving us the first direct evidence of interstellar debris colliding with a planet. Spacecraft already orbiting Mars are poised to observe. The Mars Reconnaissance Orbiter, with its sharp high-rise camera, can capture surface changes down to meter scales. MAVEN, designed to study the Martian atmosphere, can track how dust and gases interact if the comet releases material nearby. Even the aging but reliable rovers on the surface may play a role, their cameras pointed skyward to glimpse the emerald glow. For the first time in history, a planet other than Earth is serving as a frontline observatory for an interstellar encounter. Mars also offers perspective. From Earth, our telescopes peer through a blanket of atmosphere, limited by weather and light pollution. From orbit around Mars, instruments face fewer obstacles. The thin Martian air distorts light less, and the lack of city lights makes the skies darker than any place on Earth. In many ways, Mars provides a better platform for studying 3I Atlas than our own planet. The data gathered there could be sharper, cleaner, and richer than anything we can achieve from the ground. The symbolism is not lost on scientists or the public. Mars has always been a mirror for human ambition, a world we dream of exploring, colonizing, and perhaps even transforming into a second home. Now, with 3I Atlas sweeping close, Mars has stepped into the spotlight not as a distant frontier, but as an active participant in a galactic story. It reminds us that other planets are not passive rocks in space, but dynamic worlds, constantly shaped by cosmic forces. Some speculate speculate that if 3I Atlas sheds dust or gases during its closest approach, Mars could temporarily gain new layers of material on its surface. Ancient Martian ice might even interact with exotic compounds from the interstellar comet, creating chemical signatures unlike anything we've seen before. While unlikely to be dramatic on a planetary scale, even trace deposits could become invaluable clues, alien chemistry preserved in Martian soil, waiting for future explorers to uncover. For planetary defense, the encounter has a practical benefit. Mars acts as a test case. Watching how the planet's atmosphere, magnetic field, and surface respond to a close pass gives us insights into what Earth might face in a similar situation. In this way, Mars is not just in the spotlight. By coincidence, it is serving as a natural laboratory, standing in for us in a rehearsal we hope never to perform. As 3I Atlas moves past Mars, scientists around the world will hold their breath. Will the comet remain intact, or will fragments peel away and spiral into the Martian atmosphere? Will faint meteors streak across its skies, unnoticed by any eyes but those of our machines? Or will the encounter pass quietly, leaving only data, not drama? Whatever the outcome, one fact is certain. For this moment in cosmic history, Mars stands center stage. The red planet has become the spotlighted observer of an event that connects worlds, revealing that even in our small solar system, we are all part of the same unfolding story. Every comet carries with it a kind of personality, revealed through its brightness, its tails, and its chemistry. Some shine faintly, barely visible except in long exposures. Others erupt spectacularly, dazzling the naked eye. But few comets in memory have captured the imagination, the way 3I Atlas has not, because of sheer brightness, but because of its distinctive emerald hue. Across observatories and amateur telescopes, images of the interstellar visitor consistently show the same striking feature, a green glow surrounding its coma, casting it apart from the more familiar whites and blues of ordinary comets. This glow is not a trick of the eye, nor is it unique to Atlas alone. Its origin lies in the chemistry of the comet's surface and the way sunlight interacts with it. As the nucleus warms, volatile compounds begin to sublimate, releasing gases into the coma. Among these gases is diatomic carbon, or C2 carbon atoms bonded together. When exposed to solar ultraviolet light, these molecules fluoresce, emitting a vivid green light. The result is a comet that looks as though it carries its own lantern, glowing eerily against the darkness of space. What makes 3I Atlas different is the intensity of this glow. Many comets contain diatomic carbon, but here the effect is unusually strong, dominating the visual spectrum. Spectrographs confirm it. The green emissions of C2 are brighter than expected, suggesting that Atlas is unusually rich in this compound. This discovery raises questions about its birthplace. Was it formed in a colder region of its home system, where carbon could accumulate in abundance, or does its chemistry reflect conditions entirely different from those in which our solar system's comets were born? From Earth, the glow has become the defining image of the comet. Long exposure photographs show the green coma fanning outward, its tails one of dust, one of ionized gas streaming into space. To the naked eye, the color is faint, often appearing only as a diffuse smudge in binoculars. But through telescopes, the emerald hue becomes unmistakable, a ghostly beacon from another star system. For amateur astronomers, capturing this glow has become a shared pursuit, with thousands of images circulating across forums and social media. For scientists, the glow is more than beautiful, it is diagnostic. By studying its intensity and variation, researchers can estimate the abundance of carbon compounds in the comet's surface layers. They can compare it with solar system comets, building a catalog of similarities and differences. Already, it is clear that 3I Atlas is chemically distinct. Its ratios of carbon, nickel, and iron do not match what we typically see here. This suggests that planetary systems elsewhere may follow very different recipes, shaped by their star's chemistry and their histories of formation. There is also a symbolic dimension. The green glow has given 3I Atlas an identity in the public imagination. Where Oumuamua was mysterious in its silence and Borisov familiar in its cometary display, Atlas is vivid, a comet that glows with the color of life itself. Green has always been associated with vitality, growth, and renewal. To see it blazing from an object born in another star system feels almost poetic, as though the universe were offering us a reminder of connection across vast distances. Yet science scientists are careful not to let symbolism overshadow fact. The green light does not reach far. Unlike the dust tails of some comets, the C2 glow fades quickly with distance from the nucleus. It is a local phenomenon, dependent on the fragile balance between sunlight and chemistry. Still, its presence underscores the strangeness of 3I Atlas. This is not just another wanderer, but a body whose very color speaks of its alien nature. In the end, the glow may fade as the comet recedes, its volatile ices spent, its brightness diminished. But the memory of that emerald light will remain. For a brief time, humanity looked upward and saw a color carried across light years, a chemical fingerprint of another world, shimmering in our skies. The green glow of 3I Atlas will linger not just in photographs, but in the story we tell of a galaxy alive with travelers, each one bearing its own spectral signature, its own strange beauty. Every comet carries a story in its chemistry. Locked within its ices and dust are the frozen remnants of the environment in which it was born. For most comets studied so far, those environments are familiar, the outer reaches of our own solar system, where water, ice, carbon monoxide, and carbon dioxide condense in predictable ratios. But 3I Atlas has broken that pattern. Its composition is unlike anything astronomers expected, a signature not of our sun's nursery, but of a different star system altogether. Spectroscopic observations from ground-based telescopes and the James Webb Space Telescope revealed the first clues. As sunlight struck the comet, molecules in its coma began to glow, their emissions scattering across the spectrum. Scientists detected strong lines of diatomic carbon, explaining its vivid green hue. But alongside this familiar signal were surprises. Nickel appeared in unusually high concentrations, far more than in most local comets, while iron, often abundant in solar system bodies, was relatively scarce. The imbalance was striking, suggesting that 3I Atlas formed in an environment with very different chemical conditions. Carbon dioxide, too, stood out. The comet released it in large quantities, more than expected given its distance from the sun at the time. In our system, CO2-rich comets are rare, often linked to colder formation zones far from the sun's warmth. If Atlas was born in a similar region around another star, it could hint at giant planets shaping its birthplace, scattering icy bodies outward and seeding them with volatile compounds. Alternatively, it may have formed in a star system with different elemental abundances, altogether a reminder that not all planetary nurseries follow the same recipe. For astronomers, the chemistry of 3I Atlas is both puzzle and gift. Each element measured adds to the growing comparison between solar and interstellar comets. With Borisov, researchers saw high levels of carbon monoxide, suggesting formation in a frigid environment. With Atlas, the fingerprints are different: nickel-heavy, iron-poor, rich in diatomic carbon and CO2. The diversity between just two interstellar comets suggests that planetary systems across the galaxy may produce astonishingly different chemistries, shaped by their stars, their disks, and their histories of violence and scattering. The implications extend beyond comet science. Chemistry is the foundation of habitability. The ratios of carbon, oxygen, and metals in a system determine not only what kind of planets form, but what kinds of atmospheres and oceans they might one day support. To study 3I Atlas is to glimpse conditions in another system's nursery, frozen into an object that has wandered for millions of years before arriving in our skies. In this sense, the comet is a messenger, carrying whispers of alien worlds, not in science fiction, but in measurable spectra. For the public, the story of alien chemistry captured imagination. Headlines spoke of a comet with elements from another star, a body carrying exotic material across the galaxy. While the scientific details are complex, the essence is simple. 3I Atlas is different. Its chemistry does not belong to us, and in that difference lies both wonder and humility. We are not unique. Our sun is one among billions, and every system crafts its own materials in ways both familiar and strange. There is also a philosophical weight to the discovery. If comets can carry such distinct chemistries across interstellar space, then the galaxy is a place of exchange. Material is not locked within its birth system, but migrates freely, mixing, sharing, and seeding new environments. Perhaps the building blocks of life itself are carried this way, drifting until they find fertile ground. The chemistry of 3I Atlas reminds us that we are connected not only to our own solar system, but to the broader chemical story of the Milky Way. As 3I Atlas continues its journey, its Its chemistry will fade with its glow, scattered into space, but the data we collect now will remain. It is our first detailed glimpse into matter born under another star, preserved for eons and delivered to us by chance, a fragment of alien history, written not in words but in atoms and molecules, chemistry from another world. Every comet is more than an object of ice and dust. It is a record, a frozen biography of the environment in which it was born. Each layer of volatile material, each grain of dust, and each trapped gas tells a story written billions of years ago, preserved in deep cold, waiting to be read. With 3I Atlas, that biography becomes extraordinary. This is not just a relic of our own solar system's past, but a time capsule from another star entirely. The nucleus of a comet is deceptively small. For all its glowing coma and sweeping tails, the solid heart is often no more than a few kilometers across. Yet, within that compact body lies an archive of chemistry and physics. Comets form in the outermost regions of planetary systems, where temperatures are so low that even fragile ices, carbon dioxide, methane, ammonia can condense and remain stable. Over time, layers build up, each preserving the composition of its birth environment. Unlike planets, which recycle their material through tectonics, volcanism, and atmospheres, comets remain inert. They are nature's storage devices, keeping snapshots of conditions long vanished. For 3I Atlas, that means we are studying the preserved chemistry of a system we will never visit. Perhaps it formed beyond the frost line of a distant star, where giant planets stirred the disk and flung comets outward. Perhaps it was ejected during a moment of gravitational chaos, a collision of worlds, or the migration of a gas giant. Whatever the case, its biography began not here, but far away, written in a stellar nursery whose light may no longer shine. Spectroscopy allows us to read some of those pages. By splitting the comet's light into its component wavelengths, astronomers identify which molecules are present. The strong signals of diatomic carbon, the abundance of nickel, the scarcity of iron, all of these entries tell us about its environment of origin. They suggest conditions unlike those of our sun's disk, where iron was plentiful and carbon more modest. 3I Atlas carries a different balance sheet, one that hints at a chemistry, older, colder, or simply other. But comets are not static books. Their biographies evolve each time they pass close to a star. As they heat, ices sublimate, jets erupt, and material is lost into space. Each passage erases some of the record. That makes 3I Atlas particularly valuable, because this is its first and only pass through our system. Unlike solar comets, which circle the sun repeatedly, Atlas will never return. Its biography remains relatively pristine, touched by no other star since its ejection. We are reading its story fresh, the ink unblurred by repeated encounters. There is also the possibility of hidden chapters. Deep inside the nucleus, beneath the active layers, may lie ices unchanged for billions of years. These inner stores, unreachable to telescopes, could hold chemistry that tells us even more about its birthplace. Future missions, robotic probes designed to intercept interstellar comets, may one day dig into those hidden layers, retrieving pieces of biographies that now slip through our skies unexamined. For the public, the idea of a frozen biography resonates deeply. To think that a comet can hold the memory of another star system is to realize how connected the galaxy truly is. Material moves freely across light years, carrying stories like bottled letters in a cosmic sea, and for a brief time, one such letter has washed up at our shore, glowing green against the night. In the end, the biography of 3I Atlas is not only about its chemistry, it is about perspective. It reminds us that the universe is filled with ancient travelers, each carrying records of places we will never walk. To study them is to expand our sense of time, history, and belonging. This comet is not just frozen water and carbon, it is a frozen memory, drifting between stars, a biography written in ice, waiting for us to read. When people imagine a comet, they picture a single, sweeping tail, a luminous streamer stretching across the stars. But in reality, comets often carry more than one. They weave multiple threads behind them, each born of different materials, responding to different forces. In the case of 3I Atlas, those threads are unusually striking a tangled array of dust, gas, and ionized particles that shift and shimmer as it moves, leaving astronomers to unravel the complexity of its wake. The basic physics is straightforward. A comet's nucleus is a small, solid core of ice and dust. As it approaches the sun, heat drives volatile volatile ices to sublimate, releasing gases into space. These gases drag dust along, creating the glowing coma and the tails that stretch away from the sundae. But not all tails behave the same way. Dust, pushed outward by sunlight, forms one broad, curving stream. Charged particles, swept up by the solar wind, form a separate tail of plasma, often straighter and thinner. Seen together, these two create the classic image of a comet. With 3I Atlas, however, observations show more than two. Long-exposure images reveal multiple fine filaments, diverging in different directions. Some are dust-rich, scattering sunlight into faint golden hues. Others glow in the eerie green of diatomic carbon or the blue of ionized gases. Still, others appear broken, like fragments of threads cut apart by turbulence. The effect is less like a single plume and more like a tapestry, a tale of many threads, woven by forces both familiar and alien. The complexity comes from interaction. The solar wind is not steady. It gusts and fluctuates, bending and reshaping plasma tails. Magnetic fields twist and break them, creating knots and disconnections. Meanwhile, jets erupt from the comet's surface, spraying dust and gas in specific directions, forming mini-tails within the larger structure. For a comet like 3I Atlas, with an unusual chemistry and likely fragile surface, these processes can create especially vivid results. One of the most intriguing features observed so far is the misalignment of its threads. While dust tails normally arc gracefully along the comet's orbit, and plasma tails point directly away from the sun, some of Atlas's threads appear offset, as if tugged by invisible hands. Astronomers suggest that strong outgassing from volatile-rich patches may be driving these secondary tails, each one reflecting a burst of activity from a different region of the nucleus. Others point to the solar wind, particularly active in 2025, which may be reshaping the comet's emissions into multiple directions. For scientists, these threads are more than beautiful. They are diagnostic tools. By measuring their angles, brightness, and evolution, researchers can estimate the size and speed of dust grains, the strength of jets, and even the rotation of the nucleus. In a way, the tails act like instruments, recording the comet's internal processes and its dialogue with the sundae. 3I Atlas becomes not just a glowing traveler, but a dynamic laboratory, revealing its structure thread by thread. For the public, the sight of many tails adds to its aura of strangeness. Most comets already seem magical, but to see one radiating multiple glowing lines, some green, some blue, some faint and golden, gives the impression of something almost alive, unfurling banners as it crosses the sky. Photographs capture the drama, but the experience of watching the tails shift night after night is even more powerful. It reminds us that this is not a static object, but a changing one, shaped in real time by forces we can barely comprehend. In the end, the tale of many threads is both scientific and symbolic. Scientifically, it reveals the comet's chemistry, structure, and activity. Symbolically, it speaks to the richness of the universe, where even a single object can unfold into many stories at once. 3I Atlas does not travel with one thread, but with many, weaving a cosmic tapestry that links its alien past with our present sky. Every comet carries with it an element of fragility. These icy wanderers are not solid monoliths, but loose assemblies of dust, rock, and volatile ices, bound together only weakly. As they approach a star, the heat and stress often prove too much. They fracture, shedding pieces of themselves into space. Some disintegrate entirely, leaving only ghostly tails of dust behind. In the case of 3I Atlas, this possibility has loomed over every observation. Could the interstellar comet itself be fragmenting before our eyes? The idea first emerged when astronomers noticed subtle irregularities in its brightness. Night after night, the comet's glow fluctuated more than expected. While comets often brighten and dim as their jets release material in bursts, the changes in Atlas seemed unusually sharp. Some images even hinted at multiple condensation points within the coma, faint signs that more than one nucleus might be present. Such hints fueled speculation that the visitor was splitting, producing fragments too small to detect clearly, but large enough to alter its behavior. Fragmentation is common in comets from our own solar system. In 1994, comet Shoemaker-Levy 9 famously broke apart into a chain of pieces under Jupiter's gravity, each one crashing into the planet in a spectacular series of impacts. More recently, Finally, Comet 73P, divided by Schwarzmann-Wachmann 3, fractured into dozens of fragments, scattering a trail of mini-comets along its orbit. These events taught us that comets are fragile archives, easily shattered by stress. If Atlas is undergoing a similar fate, it would not be surprising, but it would be extraordinary, given its interstellar origin. The hypothesis carries major implications. If 3I Atlas is fragmenting, those pieces could become valuable in their own right. Each fragment would expose fresh material from deep inside the comet, ices untouched for billions of years. Observations of their spectra could reveal even more about the chemistry of its birthplace. In effect, fragmentation would peel back the layers of the biography we are trying to read, offering a clearer view of what lies beneath the surface. But fragments also raise risks. Depending on their size and trajectory, they could alter the dynamics of the encounter with Mars. A large enough piece could survive entry into the Martian atmosphere, creating a fresh crater, the first direct impact of interstellar material ever recorded on a planet. Smaller fragments could add dust and gases to the Martian skies, briefly changing its thin atmosphere. While Earth is not in the line of fire, astronomers note that fragment trails can persist for years and sometimes intersect with planetary orbits long after the parent comet has passed. Detecting fragments is not easy. They are often faint, hidden in the glare of the coma, or masked by dust. High-resolution imaging from Hubble and large ground-based telescopes has been tasked with the job, while spectroscopic surveys look for duplicate signals that might hint at multiple sources. As of now, the evidence remains inconclusive. What some see as fragments, others interpret as jets or clumps of dust. The comet keeps its secrets close, leaving us to wonder if its glow hides more than one traveler. For the public, the fragment hypothesis adds drama to an already mysterious story. Headlines ask whether Atlas is breaking apart, whether its emerald glow will fade or explode into a shower of smaller bodies. Social media fills with side-by-side comparisons, as amateur astronomers scrutinize images for faint extra points of light. The idea that the interstellar visitor might split makes it feel alive, vulnerable, and unpredictable. Whether or not 3I Atlas is fragmenting, the possibility highlights its fragility and our fleeting opportunity to study it. If it remains intact, we will learn about its surface and its chemistry. If it splits, we may glimpse its interior. Either way, the comet is teaching us about the nature of interstellar matter. It is not eternal, not invincible, but fragile, temporary, and precious. The fragment hypothesis may or may not prove true, but as long as the question remains, astronomers will watch more closely, knowing that each night could bring the moment when a single comet becomes many. When it comes to cosmic debris, Earth has always seemed like the prime target. Our atmosphere burns meteors into streaks of fire, and our oceans and continents bear the scars of ancient impacts. But in reality, no planet in the inner solar system collects as much evidence of cosmic encounters as Mars. With its thin atmosphere, its relatively exposed surface, and its position close to the asteroid belt, Mars has long been a natural collector of wandering material. And now, with 3I Atlas passing nearby, that role has come into the spotlight once again. Mars's thin atmosphere is the key. On Earth, the blanket of air acts as a shield, vaporizing most small meteoroids before they can strike the surface. Only the larger ones survive the plunge, and even then, the impact craters are weathered away by wind, water, and tectonics over millions of years. Mars, however, lacks such protections. Its atmosphere is less than 1% the thickness of Earth's, offering little resistance. Even small fragments can reach the ground intact. As a result, the Martian surface is pockmarked with craters of all sizes, from massive basins carved by asteroids to tiny, fresh scars no wider than a few meters. Orbiters such as the Mars Reconnaissance Orbiter have confirmed just how active Mars is as a collector. By comparing images of the same region taken years apart, scientists have identified new craters forming regularly, sometimes dozens each year. These fresh scars are often surrounded by dark ejecta, proof that small fragments of rock, only a meter or two wide, are still striking Mars today. It is a silent rain of space debris, ongoing and relentless. With 3I Atlas approaching, astronomers began to wonder, could Mars collect pieces of this interstellar traveler too? If the comet were to shed fragments as it neared the Sun, Mars would be well positioned to intercept some of them. Even a tiny shard, no bigger than a rock, could leave behind a fresh crater. crater. The significance of such an event would be profound. For the first time, we might see physical evidence of interstellar matter embedded in the surface of another planet. A crater on Mars caused by Atlas would not just be another scar, it would be a galactic fingerprint. Even without direct impacts, Mars still plays its role as a collector in another way, as an observatory. Its orbiters and landers can record the effects of passing dust and gas, capturing traces of alien chemistry as they drift through the planet's skies. Instruments designed to study the Martian atmosphere might suddenly find themselves analyzing carbon compounds or metallic ions carried from Atlas's coma. Mars becomes not just a receiver of impacts, but a sampler of interstellar particles. The symbolic weight of this is enormous. Humanity has long dreamed of sending people to Mars, of making it our second home. To imagine that Mars itself might be collecting material from another star system while we prepare to set foot there adds another layer of meaning. It transforms Mars from a destination into a participant in a larger story, a stage where the galaxy leaves its marks. For planetary defense experts, Mars's role as a collector is also instructive. Studying the rate and scale of impacts there helps us estimate risks for Earth. By tracking how often Mars is struck and by what size objects, we refine our understanding of how crowded the inner solar system truly is. And with Atlas in the picture, Mars offers a natural experiment. How does a planet respond to the passage of an interstellar comet? In the end, Mars does what it has always done. It collects dust, fragments, meteoroids, even whispers of chemistry from beyond. Its surface is a museum of impacts, a record of billions of years of encounters that Earth has largely erased. Now, as 3I Atlas sweeps past, Mars may add a new exhibit, a reminder that the red planet is not just a world we observe, but a witness, a collector, and a keeper of stories that stretch beyond the solar system itself. From the ground, the arrival of 3I Atlas is more than just another astronomical event. For Earth, the perspective is layered at once scientific, cultural, and personal. Our instruments measure its chemistry and motion, but our imaginations grapple with what it means to see something born under another star glowing in our skies. Few cosmic events have so neatly bridged the gap between raw data and human wonder. Astronomically, Earth is uniquely placed to study the interstellar comet. Our telescopes, both ground-based and spaceborne, can track it across the sky, capturing light that has traveled millions of kilometers in order to reach us. The James Webb Space Telescope, orbiting far beyond Earth's atmosphere, dissects that light into spectra, revealing the comet's unusual chemistry. The Hubble Space Telescope, though aging, still delivers high-resolution images of its coma and tails. On the ground, facilities like the Very Large Telescope in Chile and Keck Observatory in Hawaii add their perspectives, each sharpening the picture of a comet that will never pass this way again. For amateur astronomers, Earth's perspective is equally important. Across continents, observers point cameras and binoculars toward the faint green glow. Some see only a smudge, others capture intricate photographs, revealing tails and threads invisible to the naked eye. The collective effort becomes global, with images and measurements shared online, creating a patchwork portrait stitched together by thousands of eyes. In this way, Earth is not just observing through machines, but through the participation of countless individuals connected by curiosity. Culturally, the view from Earth resonates in ways that go beyond science. From ancient times, comets have carried symbolic weight, omens, messengers, disruptions of the ordinary. To know that this one comes not from our solar system but from another star adds a new dimension. It is not just a local wanderer, but an interstellar emissary, a reminder that the cosmos is larger, stranger, and more connected than our daily lives suggest. In headlines and conversations, people speak not only of its chemistry but of its meaning, asking what it says about our place in the galaxy. There is also humility in Earth's perspective. We know that the comet does not care for our stories. It follows a trajectory set millions of years ago, long before humans walked the Earth, and will continue on its way long after we are gone. Its presence is indifferent, but our awareness transforms it into something more. By naming it, studying it, and reflecting on it, we weave it into the human story. In a way, comets remind us that perspective itself is our gift, the ability to look outward, to see something alien, and to wonder. For planetary defense experts, Earth's perspective carries practical lessons too. Though 3I Atlas poses no threat, its passage reinforces the reality that our skies are never empty. Asteroids and comets pass constantly, most small and harmless, but some large enough to matter. By tracking Atlas so closely, by testing our networks of observation and communication, we refine the skills that might one day protect us. The interstellar visitor thus becomes part of Earth's quiet rehearsal for challenges we hope never to face. Perhaps the most profound aspect of Earth's perspective, however, is the sense of connection. As people across the globe step outside to watch the comet, they are united by the same sky. In an era often marked by division, here is something shared, a faint green light that belongs to no one nation, no one culture, but to all. For a few moments, we are reminded that we live on the same planet, orbiting the same star, under skies that can still surprise us. In the end, Earth's perspective is not just about what we see, but how we interpret it. To scientists, it is data. To storytellers, it is symbolism. To individuals, it is wonder. And, together, those layers form the true meaning of 3I Atlas for our world. From Earth, we see not only a comet, but a reminder. The universe is alive with travelers, and we are fortunate enough to witness their journeys. For astronomers, one of the greatest frustrations of comet observation is not distance, but brightness. Not the glow of the comet itself, but the overwhelming brilliance of the Sunday. Many of the most important moments in a comet's journey, including its closest approach to the inner planets, happen when it lies near the sun in our skies. At those times, the object becomes almost impossible to observe directly, lost in solar glare. 3I Atlas, in its passage through the solar system, has already tested the limits of what we can see and what we cannot. From Earth, the sun's light dominates everything. Its glare drowns out faint objects within tens of degrees of its position. Telescopes designed to block out this interference, such as coronagraphs, help, but their fields of view are limited. That means that during critical windows of 3I Atlas's path, the comet is effectively hidden from direct observation. To the casual stargazer, it seems to vanish altogether, a ghost swallowed by daylight. For scientists, those missing days or weeks are gaps in the record intervals when the comet may be undergoing changes we cannot witness. Space-based instruments offer a partial solution. The SOHO spacecraft, stationed at the L1 Lagrange point, carries a coronagraph that blocks the sun's disk, allowing faint objects nearby to appear. Over the years, SOHO has discovered thousands of sun-grazing comets this way, most too small to survive their encounter with solar heat. As 3I Atlas moved toward the sun's neighborhood, SOHO and its successors, like Stereo, became crucial tools for monitoring its progress. Yet even they are limited. Comets as faint and diffuse as Atlas are easily lost in background noise, appearing only briefly before slipping into invisibility again. This period of invisibility is not without scientific value. By comparing data before and after the comet passes behind the sun's glare, astronomers can infer what has changed. Has the comet brightened, suggesting fresh outbursts of gas and dust? Has it dimmed, hinting at fragmentation or depletion of volatile ices? The missing days serve as a kind of before and after snapshot, even if the crucial middle remains hidden. There is also risk in this disappearance. If 3I Atlas were to fragment while near the sun, the event might go unobserved, leaving only the aftermath visible when it reemerges. In such cases, debates would rage. Did the comet survive intact, or has it already shed pieces that are now scattered, unseen through space? The lack of continuous data becomes fertile ground for speculation. For the public, the idea of a comet hidden in sunlight carries a different symbolism. It feels almost mythical, a traveler that vanishes into brightness, then reappears transformed. Across cultures, comets have long been tied to omens and transitions. To see one disappear into the sun's glare and then emerge again echoes those old narratives, even as science offers natural explanations. For scientists, though, the frustration is practical. Missing data can mean missed opportunities. If outbursts occur unseen, if tails shift, or if chemistry changes, those events may be lost forever. Each interstellar comet is a once-in-a-lifetime chance, and every missing observation stings. Researchers mitigate this by using every available tool: radar, solar observatories, automated sky surveys, and even instruments aboard Mars orbiters, which view the sky from different vantage points. Together, they stitch a patchwork of data around the gap. When 3I Atlas emerges from the sun's glare, attention sharpens. Observers search for signs of change, new tails, altered brightness, or evidence of fragmentation. The comet's reappearance is always dramatic, whether it emerges brighter, dimmer, or in pieces. Whatever the outcome, the moment underscores a truth about our perspective. The sun, giver of life and light, also blinds us, hiding stories unfolding just beyond its glow. In the case of 3I Atlas, its time hidden in the glare is not absence, but anticipation. We wait, instruments ready, eyes scanning the bright horizon, and when it re-emerges, we know we are witnessing not just a comet, but a survivor, one that has passed close to the heart of the solar system and returned to tell its tale. Astronomy has always advanced hand in hand with technology. Every leap in instrumentation, from Galileo's first telescope to space-based observatories, has opened the universe wider. The arrival of 3I Atlas has coincided with another leap forward, one that has given us new eyes on the sky. Unlike its interstellar predecessors, Oumuamua and Borisov, this comet is being observed in an era of unprecedented capability, and that fact alone has changed the story. The most transformative development is the Vera C. Rubin Observatory, nestled high in Chile's Atacama Desert. Though still in the early stages of its survey, Rubin represents a revolution in skywatching. Its massive mirror and wide-field camera can capture enormous swaths of the sky each night, cataloging faint objects that previous surveys would have missed. Many of the asteroids and small bodies discovered during the same season as 3I Atlas are owed to Rubin's watchful eye. Without it, the apparent parade of objects might have gone unnoticed, dismissed as background noise instead of recognized as a pattern. Rubin is not alone. The James Webb Space Telescope has given astronomers the power to dissect faint, distant light into exquisite spectra, revealing chemical fingerprints across infrared wavelengths. For 3I Atlas, Webb has confirmed its unusual chemistry, the high abundance of nickel, the distinctive ratios of carbon, and the strong emissions of diatomic carbon responsible for its green glow. These data provide details beyond what ground-based telescopes can achieve, offering a richer biography of the comet's origins. Meanwhile, smaller observatories, both professional and amateur, have played their part. Networks of robotic telescopes across the globe, linked through automated software, provide continuous coverage as Earth rotates. Amateurs with sensitive cameras contribute images night after night, building time-lapse records of the comet's evolution. Never before has an interstellar object been tracked with such breadth of participation. In a sense, new eyes doesn't just mean new machines, it means new levels of collaboration. Mars, too, adds its perspective. Orbiters like MAVEN and the Mars Reconnaissance Orbiter provide views from outside Earth's atmosphere, while rovers may glimpse the comet from the ground. These Martian instruments extend our eyes beyond Earth itself, turning another planet into part of our observational network. It is a reminder that the frontier of astronomy is no longer confined to one world. For planetary defense, the value of these new eyes cannot be overstated. The same systems that track 3I Atlas also guard us against threats. The fact that so many small asteroids were discovered in the same season is not necessarily alarming. It is reassuring. It shows that our detection capabilities are catching what once would have slipped past unseen. Every object tracked refines our models of orbital dynamics, giving us confidence that should a genuine threat appear, it will not catch us unprepared. There is also a philosophical weight to this moment. When Oumuamua appeared in 2017, we were caught off guard. Its faintness, its speed, and its strange behavior meant we had only weeks to observe it before it slipped away. Borisov in 2019 gave us more time, but still only limited data. With 3I Atlas, the story is different. Discovered earlier, studied with more powerful instruments, and observed by more eyes than ever before, this comet represents a turning point. Humanity has finally reached a stage where interstellar visitors cannot pass unnoticed. For the public, the phrase "new eyes on the sky" feels fitting. It captures the sense that we are not just looking more deeply, but more widely. The galaxy is not static, it is alive with wanderers, and our tools have grown sharp enough to see them. Each detection affirms that we are part of a vast system of exchange, where material moves freely between stars. In the end, these new eyes do more than reveal 3I Atlas. They remind us of what comes next. Other visitors will arrive, perhaps sooner than we expect, and when they do, we will be ready, armed with instruments capable of turning faint smudges into stories, transforming anonymous dots of light into known travelers with histories, chemistries, and tales to tell. When most people hear the phrase planetary defense, they imagine science fiction scenarios, giant lasers, nuclear weapons, or heroic missions to push asteroids aside. The reality, however, is far quieter and far more precise. Planetary defense is not about sudden, dramatic interventions. It is about careful watching, relentless tracking, and the patient refinement of orbits. And in 2025, with 3I Atlas moving through the solar system and a surge of small asteroids appearing around the same time, planetary defense shifted from theory into practice. At its core, planetary defense begins with discovery. Networks of telescopes across the globe, from the Atlas Survey in Hawaii to Pan-STARRS, from the Catalina Sky Survey in Arizona to the newly active Vera-C. Rubin Observatory in Chile sweep the skies every night. Their goal is to find faint, fast-moving points of light that reveal new asteroids. Once detected, the object's position is compared across multiple nights, allowing astronomers to calculate its orbit. This step is crucial. Knowing where a body is and where it is going is the foundation of planetary defense. With 3I Atlas, the situation was different. Its hyperbolic path made it no threat to Earth, but its arrival sharpened the system. The unusual clustering of asteroids in the same season forced tracking networks to work at full capacity. Each new discovery was logged with the Minor Planet Center, where teams of scientists analyzed potential impact risks. Automated algorithms ran probability checks, projecting trajectories decades into the future. Even when the odds were vanishingly small, the exercise mattered. It proved that our detection systems were not only active but responsive. The recent success of NASA's DART mission, the Double Asteroid Redirection Test, added another layer to this practice. In 2022, DART intentionally struck the asteroid moonlet Dimorphos, altering its orbit by measurable amounts. It was the first demonstration that humanity could deliberately change the path of a celestial body. With that proof in hand, planetary defense had moved beyond theory. Now, as 2025 unfolded, astronomers imagined how such methods might be scaled should a future object present a real threat. For Earth, practice means preparation. The European Space Agency's Hera mission, set to follow up on DART by studying the Dimorphos system in detail, will provide even more data on impact physics. The Planetary Defense Coordination Office, a relatively small but vital branch of NASA, continues to refine its global communication protocols, ensuring that if a threat were detected, governments and agencies could act quickly and with clarity. In this sense, planetary defense is as much about coordination as it is about technology. The arrival of 3I Atlas has been an ideal test. Even though it posed no risk, it reminded the public that the solar system is never static. Dust, fragments, and asteroids move constantly, their orbits shifting under gravitational nudges and solar winds. The apparent parade of asteroids alongside Atlas underscored how quickly the sky can become busy. Tracking them all was not just an exercise in curiosity, but in readiness. For the public, the notion of planetary defense often inspires unease. The very idea that Earth could face a dangerous impact is unsettling, but the practice itself is reassuring. The fact that we are watching, cataloging, and preparing demonstrates that the threat is manageable not by chance, but by vigilance. When people saw headlines about Atlas and the surge of asteroids, they were also seeing proof that humanity is building the tools to protect itself. Philosophically, there is something profound in the concept of planetary defense. For most of Earth's history, impacts shaped evolution without warning. Dinosaurs were undone by a rock from space. Ecosystems were changed by craters. Humanity, however, stands at a turning point. For the first time, a species on Earth has the ability to anticipate such events and even prevent them. In that sense, planetary defense is not just a technical field. It is a declaration of responsibility, a recognition that we are custodians of our planet with the knowledge and tools to defend it. In practice, the arrival of 3I Atlas has been a rehearsal, not a crisis, but rehearsals matter. Each calculation, each test, each coordination effort brings us closer to readiness. One day, when a genuine threat emerges, it will be these quiet practices, not heroic last-minute saves, that make the difference. When we think of space, we imagine stars with their families of planets, moons, and comets bound tightly by gravity. But not everything belongs to a star. Some objects drift freely, unbound, roaming the vast distances between suns. These are the wanderers, icy comets, rocky asteroids, and even planets flung from their birthplaces. 3I Atlas is one of them, an interstellar traveler whose path carries it through our solar system only once before it disappears forever into the dark. The story of such wanderers begins in planetary nurseries. When stars form, they are surrounded by disks of gas and dust. Within these disks, matter clumps into planets, moons, and smaller icy bodies. But this process is chaotic. Giant planets shift positions, pulling on comets and asteroids, scattering them like debris from a construction site. Most stay bound to their star, orbiting at great distances. Some, however, are launched with enough speed to escape entirely. Once freed, they become interstellar wanderers, destined to travel the galaxy alone. Astronomers believe the Milky Way is full of these exiles. For every star system, trillions of small bodies may have been ejected over billions of years. Most will drift unseen, too faint to detect. Only when one passes close to a star, like our sun, does it flare into visibility, lit by starlight, or warmed into releasing gas. The detection of just 3 interstellar objects in less than a decade, Oumuamua, Borisov, and now 3I Atlas, suggests that they are far more common than once thought. The galaxy is not empty, but alive, with countless wanderers crossing paths. The nature of these wanderers is diverse. Oumuamua was rocky and strange, showing no tail but accelerating as if pushed by invisible forces. Borisov was more familiar, resembling a comet from our own system, but with unusually high carbon monoxide. 3I Atlas, with its vivid green glow and nickel-rich chemistry, adds yet another kind to the catalog. Together, they reveal that the galaxy's planetary systems do not follow a single template. Each star leaves behind travelers shaped by its unique conditions, and those travelers eventually pass through other skies, carrying the memory of their origins. For astronomers, the wanderers are gifts. They bring samples from places we cannot visit, carrying chemical signatures of distant stars. They confirm that planetary formation, the process that created Earth, is happening everywhere, under different recipes and rules, and they raise deeper questions. Could some wanderers carry the building blocks of life? Could interstellar comets spread organic molecules across the galaxy, seeding planets with the potential for biology? If so, then wanderers are not just travelers, they are messengers of possibility. For the public, the idea of wanderers resonates on a human level. These objects, adrift and alone, mirror our own curiosity about exploration and exile. They remind us that movement is part of the universe's fabric. Stars orbit the galaxy, planets orbit stars, and some bodies travel untethered, free of all bonds. In their loneliness, people see mystery. In their persistence, they see resilience. To witness one with our own eyes, to watch 3I Atlas glide past Mars and Earth, is to feel the scale of the galaxy made real. There is also humility in recognizing wanderers. They remind us that our solar system is not isolated, not sealed off from the rest of the Milky Way. We live in a place that is open, porous, connected to the galaxy through countless unseen threads. At any moment, another wanderer could appear, crossing our sky, carrying with it new chemistry, new questions, and new stories. As 3I Atlas continues its passage, it embodies this truth. It is not just a comet, not just an object glowing green against the stars. It is a traveler, a wanderer between the stars, whose journey stretches across distances we can barely imagine. And for a brief time, it has chosen our skies as part of its endless road. Every interstellar object carries a clue about where it came from. Its speed, its angle of approach, and its chemistry act like fingerprints, pointing back toward the region of the Milky Way that may have birthed it. For 3I Atlas, those clues suggest an origin in a part of our galaxy rarely in the spotlight, the thick disk. To understand this connection, it helps to picture the Milky Way's structure. Our galaxy is not a flat, uniform sheet of stars. Instead, it has layers. Closest to us is the thin disk, home to most of the bright stars, nebulae, and ongoing star formation we see in the night sky. Beyond it lies the thick disk, an older, puffier layer, populated by stars that are ancient, metal-poor, and slightly tilted compared to the thin disk. Encompassing both is the vast halo, a sparse sphere of scattered stars and dark matter. The thick disk is a kind of fossil record of the galaxy's early years. Its stars are more than 10 billion years old, born in an era when the Milky Way was young and chaotic. Back then, supernovae erupted frequently, enriching the interstellar medium with heavy elements. The chemistry of thick disk stars reflects that violence. High levels of certain metals, but different balances compared to the younger thin thin disk. If 3I Atlas truly comes from this region, then it is a relic of that ancient time, a frozen fragment from a galactic epoch long before the sun was born. Evidence for this link comes from two directions. The first is orbital velocity. 3I Atlas is moving faster and on a steeper angle than most stars in the thin disk, but its motion matches well with populations in the thick disk. Astronomers use simulations to trace such hyperbolic paths backward, and while uncertainties remain, the kinematic fit is striking. The second clue is chemistry. Spectra of Atlas show an unusual abundance of nickel compared to iron, a ratio that aligns more closely with the enrichment patterns of thick disk stars than with solar system bodies. In other words, its makeup looks less like us and more like them. If this connection is correct, the implications are profound. We are not just looking at an interstellar comet, we are looking at material ejected from one of the oldest neighborhoods in our galaxy. The thick disk is a place we cannot visit, its stars too far away for spacecraft, its chemistry studied only in starlight. Yet here, by chance, a fragment of it has crossed our path, close enough to study in detail. It is as if a piece of galactic history has been hand-delivered to our doorstep. For planetary scientists, this adds a new dimension to the study of cometary diversity. Oumuamua may have come from one region, Borisov from another, and now 3I Atlas points toward the thick disk. With each interstellar object, we sample a different galactic environment, building a patchwork of planetary formation across the Milky Way. Already, the differences are striking. Borisov was carbon monoxide-rich, Atlas is nickel-heavy, and Oumuamua defied easy classification altogether. These contrasts suggest that no two planetary systems are alike, and that the Milky Way is a laboratory of endless variety. For the public, the phrase thick disk connection may sound abstract, but the meaning is simple. This comet is old. It may have formed when the galaxy was half its current age, when stars were fewer, brighter, and more violent. Its journey to us may have taken billions of years, drifting silently through interstellar space before arriving here. To see it glowing green in our skies is to witness a relic of galactic antiquity, a fragment of a time when the Milky Way itself was still young. In the end, the thick disk connection transforms 3I Atlas from a curiosity into a messenger. It is not just passing through, it is carrying a story from another era, a record of conditions that shaped the galaxy's history. By studying it, we are reaching across both space and time, glimpsing the ancient heartbeat of the Milky Way, written in ice and dust. As we follow the trail of 3I Atlas, we are reminded of something greater than the comet itself. The emerald glow, the fragments, the asteroids, the shifting patterns around Mars, all of it points to one truth. The solar system is not an island. It is part of a galaxy alive with motion, where stars, planets, and comets share their histories across light years. Every observation of Atlas is more than data. It is a story of chemistry born in another star system, of journeys lasting billions of years, of encounters that connect us to a wider cosmos. For a brief moment, we are witnesses to that story, watching an interstellar traveler leave its mark on our skies. The comet will not stay. Soon it will fade into distance, continuing its endless voyage beyond the sun's reach. But what it leaves behind, the knowledge, the wonder, the perspective, will remain with us. It has shown us that the universe is open, connected, and full of surprises. And before we close, make sure you're subscribed so you don't miss the rest of these journeys. Share in the comments where in the world you're watching from, because just like the wanderers of the galaxy, we too are connected across distance, all under the same sky.